All right, so just remember kind of like what we saw from last class, right? Was like that there's these two different, strategies that are similar but are actually pretty different. Um, so right, the first one is just like replication, right? Meaning like we literally have the exact same data in two different locations, and we said there's like three different reasons uh, for doing this. So one is just like geographic, if we have users in different locations. Two is like throughput, right? Meaning, and this is kind of, well, let's do that one last because it's the most kind of tricky one. And then the second one is like durability, meaning like if one of these nodes goes down, especially with a user-facing application, right? If one of like our databases go down, we want to make sure others are still working, right? And then they also have the data, right? So, and then throughput is just the ability that, especially again with like consumer facing applications, that we can read from the database quickly, and also that we can, or I should say, that we can write to the database very quickly. And depending on the databases, some are optimized for reads, some are optimized for writes. You can like look at more extensive like system design videos or material to like see the ins and outs of that. It turns out for analytical databases, throughput, as you can imagine, is not really a big deal, especially when it comes to writes, because we're loading our data in batches, right? We don't really have, we're not really dealing with like fast transactions. We're dealing with like once a day, offline kind of performing some analytical queries most of the time. I mean, there can be exceptions if you're, say, doing like cybersecurity, for example, or where you want to make sure that, the moment that someone hacks in, that there's an alert. And how might you do that is by querying, right? That you might need like a streaming database and have some query set up to it that when you see the sequence in the logs, that you then, shut down that user or whatever, right? So it does happen, right? But in kind of, but most of that kind of work won't be with like pure data engineering. It will be in kind of like, honestly, like either more senior level data engineering or something fairly specialized. For the work and the questions that you'll get, the throughput is not really significant for us. If you just think about the kind of work we did, it's offline, right? It's like a day later, or even if it's an hour later, it's not a big deal. Same thing, like durability. We don't really need, as a data engineer, like a separate node oftentimes up and running for the purposes of durability. We don't necessarily need that because we can snapshot the data, and that generally works fine. You don't really see databases other than doing that. They don't really worry about it too much. And then same thing with geographic purposes. Like we don't have to always optimize for latency, and typically the teams are in like a single location, or we could just copy the data. Again, because things are happening offline, these things just don't cause the same kinds of problems as they do when we both need, where with like a consumer facing or an OLTP, where we both need our data to be up to date by like the millisecond and consistent, right? Like this is very challenging because it takes time to say, if we say write to this database, then copy that data over to here, right? That second can cause a problem if you're doing, say, like a banking application, right? Which I gave in that was my example from the last class, all right? So that's replication. Instead, what our analytical databases typically, what we'll see is more, they will handle like how do we get faster reads, and that they do through partitioning, right? Where partitioning is really not using like two different databases or two different servers necessarily, or I shouldn't say, is not using two different servers with the same exact data on it, but taking that data and splitting it up. And I'll now go to the diagrams because they're better than my drawings. But the way that occurs, as you've kind of seen, is with something like this, right? So this is what we described as redshift. And the partitions, like in practice, they occur both on the same machine and also between machines, okay? So what I mean is, like here I just show like one partition, one machine just has like one partition, and you can imagine, this all holds the movies data set and it's across 4 machines. But in practice, what occurs on something like Redshift is that you can have a partition, you can have like, let's say there's 4 cores on a single CPU and you have 1 CPU on your computer, you can have 4 partitions, right? Per each node. And you can have 4 partitions here, 4 partitions here, 4 partitions here. What is the benefit of this? There's 2 main benefits, okay? One is we get just like fast lookup, meaning if you're looking for movies from a certain year and we are partitioning by year, we don't have to query our entire data set. We can just go to the partition that's holding the movies from that year, okay? So the first benefit is just fast lookup. The second benefit, which is kind of illustrated here, is concurrency. And here, what I'm showing is an example of that, which is MapReduce. So there's 2 different ways you can think of concurrency. One is, let's say we get like, as somebody's looking up movies from like 2005, we're also performing the queries to look up movies from 2010. And if those are located on 2 different partitions, it means that a different CPU core is responsible for that query. Each CPU core gets its own partition, or I should say each partition is allocated its own CPU core. So we can perform those 2 queries simultaneously, right? One thread will do one, the other CPU core will do the other. So that's one thing, is we can like literally serve 2 different queries simultaneously because we're just taking advantage of different CPU cores. The other thing is kind of like divide and conquer approach, which we call MapReduce, for a single query, right? And this is kind of more classically what people will talk about and kind of like what you're taking advantage of. And that's the idea of, if we want to see like what's the average year or across all movies, we don't have to have one core kind of like read through the entire data set. Instead we can split the data set up 16 ways. That's done, prior. And then each core is querying its own partition of the data, sending back the results, right? The average year, probably along with the number of rows. And then we just do a weighted average, right? And the way that and that's called MapReduce, right? The mapping part is the fact that each core or each partition is answering the same exact question, right? Performing the same computation. What is the average year? And then the reduce is then reducing those responses from each of the partitions. Does that make sense? What the MapReduce strategy is? Let me. Is there any side effect of partitioning? Are there any other considerations other than deciding which columns to partition on? I mean, you can only partition based on the main thing is, you will be deciding how many partitions to use. I think you can kind of decide that, and they will, but I don't think there's any downside to just using the maximum number available, and that would be fastest. The biggest question typically is that question of like which partition columns do you use? I think this is called, I forget in Redshift, I said it last class, I think it's called like the distribution key. That is typically like a pretty big question, or somewhat significant. You want to put some thought into it, because let's say we're searching for movies in 2006, and I talked about this last class, right? If we're searching for like what's the average length of movies in 2006, if you're partitioning by year, that's great, because all those movies are right here. You send it back, you're done. If you're partitioning by if you're partitioning by, let's say, genre, that means some of the 2006 movies are over here, some of the 2006 movies are here, blah, 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 right? And that means now you have to query all these, and you might say, well, I get this map reduced, we get to do it at the same time. The downside is now we have to wait for each one of these guys to respond, so you have to wait for the last guy to respond. And typically, it's the network, it's like sending this data through the wires, that can take a while. The other thing is, and I think Redshift may do this. I'd have to look it up. But there's some databases, I think Redshift may perform that last computation, not like the reducing component, not in this leader nodes, but in one of these nodes. So you're like sending data to, like compiling it all in a single node. And you guys can just Google it. That's called shuffling. All right, so you can just Google it, like how to tell me about shuffling and Redshift and how I can avoid it with partitions. But that's basic. That is the idea, is that you want to avoid having to, query data from separate nodes if you don't need to, right? And so the way that you do that is, it's not like you say, well, I just won't ask that question. You just choose your partition key based on something you normally query by, right? Or normally like query by, I mean like filter by. So when you do where, what is that where clause normally, what column normally comes after that where clause? Is it where the date is a certain thing? Is it where the genre, etc.? Okay, so that's like the biggest kind of consideration when you're partitioning, is just what column are you partitioning by, and you're doing it such that what you are used in your where clause, that's typically your partition column. Okay, and then kind of we did talk about, and I think it came up with Conwell. There are a couple other considerations you can kind of get into. Another one would be like data skew, right? And there's a reading, right, also that goes into a little bit more detail. So like you want these partitions roughly to be the same size, right? So like that means, for example, let's say you're partitioning by somebody's last name. You don't want to give each letter of the alphabet, right, an equal partition, because we know that they're not at all evenly distributed, right? So data skew is something else you can worry about. But that's why date typically does work. So one way you can do that is like a good column. So date typically works pretty well because it's fairly even, although maybe not by day, but you can think of Christmas or things like that, but by year, you'll be pretty good. And then the other thing we talked about is like map-based partitioning. So there's like two main different kinds. There's what we've been talking about so far, which is range-based partitioning. And with that, you literally say, okay, from 2000 to 2005 is in one partition, etc. With map-based partitioning, you take somebody's last name, Smith, you feed that through the hash function, or I should just call this hash-based, sorry. You feed that through your hash function, of Smith. That spits out basically a location, and so it will then send Smith maybe will be assigned partition X, right? And then somebody else. And the idea, oftentimes these things kind of appear random, and that's on purpose, right? Because you want a benefit of hash-based partitioning is it should have fairly even distributions, right? So Smithy would be in partition Y or whatever. So this is another kind of alternative you can do, and you can kind of like you can get into this if you want to. Like you can Google some other things. These are the main components that you think about. So it's like data skew is kind of secondary, I'd say. The first would be like, are you partitioning by what you are typically querying on? And by the way, this is the same rule for indexing too, right? You don't want to index on a column that you never query on. So if you're never querying on like what the guy's last name is, don't index on their last name, right? Index on something you are querying on, okay? Cool. So these are the main considerations. Partition on what you typically query on. Consider data skew, meaning some partitions have drastically more data than the others. And just think practically why that's an issue. If you have 1,000 in one partition and like 3 in the other, right, you're dictated by your slowest partition, right? You have to go through all of that, which 1,000 is a big deal, isn't a big deal, but if it's 100,000, a million, that's a bigger deal. So you're dictated by the largest partition, right? And that's going to be your slowest one. So it's best if these things are more evenly distributed, right? And one way to achieve that is like hash-based partitioning. You can do that. Cool. All right. So this is how Redshift works. Redshift, I believe you do have to specify the partition key. I don't think it might just do something random for you, but typically you specify the partition key if you're trying to take advantage of this. Yeah, and it has leader nodes, and then these are the compute nodes, and this is basically how it performs MapReduce. We talked about the fact that, okay, what is kind of nice about this? What was the idea of this back in 2016 or so, 2017? Which wasn't that long ago. The idea was like, okay, cool. Like as we scale our data, not only we're naturally scaling our compute, which seems like a good idea. The downside of this is that it's not necessarily the case that just because you have more data, you want to be paying for the memory and CPU. This is the most expensive part, the memory and CPU. So it can be nice, right, if we can have all of our data, but if I'm just like, a data team of 1 or 5 and we're okay with slower queries, or just like kind of, we don't always need 4 times as much compute just because we have 4 times as much data. It would be nice if we have that option. That's kind of one of the main benefits of Snowflake, okay? So here, you can think of this as isolated compute, okay? So here we call this shared nothing architecture, right? Because each CPU, each processing gets its own data, right? We're not sharing the resources across data sets, just each partition gets its own data. Here, this is isolated compute, and by that I mean we have the storage layer. There is no computing resources in this. This is a hard drive, okay? And then we're just storing all of our data. And then if we want to query the data, we have what's called, Snowflake calls this a data warehouse. What is this really? It's an EC2 machine, all right? So you have an EC2 machine connect to the underlying data, and the query processing power lives here on the EC2 machine. What's nice about this is, say I'm just one team, I'm a guy in marketing, I want to query my analytics database, I can spin up an EC2 machine, connect to the storage layer, and get back my data. If I'm like, now we have my marketing team, and then we build on, the finance team, and we want to give them access, right? I can just add another EC2 machine, connect that to the storage layer. By the way, what is the storage layer really? It's S3, okay? So we're storing the data in S3, and Snowflake is managing all this for you. You just click on Snowflake and add some data, and you write in your queries. And I have the curriculum if you want to see the interface and how it works. But underneath, when you say, hey, I want to spin up a data warehouse, it's spinning up an EC2 machine or some computing power for you, and then using that computing power to query the S3 where the data lives. All right. You can see this is a full computer, so you do have hard drive memory, but the main thing is the CPU, which is what's performing the query. And like I said, what's nice about this is if you have a little bit of data, but you have a lot of people making queries, you can just add more data warehouses. If you have a lot of data, but not a lot of need for processing power, you can just have a single EC2 and you're fine. Okay, so that's kind of like one of the main innovations of Snowflake is just this idea of isolated compute. Any questions about that part? So I said, okay, with isolated compute, we basically avoid these two issues. So one was concurrency, like the idea that we wanted to be able to perform multiple queries at the same time, right? This guy can perform a query, this guy can perform a query. The other is just we don't have to scale our compute as we scale our storage layer. The other thing I should say is Snowflake can perform MapReduce just like Redshift can, right? So the fact that we have multiple cores, right, on a single CPU, it can query the proper S3 partitions in S3, and each core can query a separate one, a separate partition, and then send back the results. I think there was a question. Let me just see it. Okay. Is it a separate EC2 for each individual database? No, so you can have, let me get into that in the next lesson, but basically you can have, Snowflake has this idea of a data warehouse, and a data warehouse is like, kind of, you think of that as like, this is your computing power, all right? So it could be, you basically like log into the data warehouse, or you log in and you kind of have to access a data warehouse in order to perform the query. And it could be like one team has this data warehouse, or it could be, and the data warehouse is just an EC2 machine. Or if you want, it can also be, you can just scale this single data warehouse as much as you want. So it can be a cluster of EC2 machines too. So yeah, it's not this storage layer. You can think of this as the database, really, or or really like, honestly, conceptually, it should be this whole thing is the database. But when you log in, you need to have the authentication to, access this data warehouse, right? And it just like checks who did you log in as. You can access this data warehouse, and then from this data warehouse, you get to query this. What is the benefit of like giving marketing a separate data warehouse than say finance? There's different things. Maybe we have different authentication, right? Like finance is able to access data that marketing isn't, and vice versa. The other thing is oftentimes like budgeting costs, right? Like they might have different budgets, and so like, yeah, we want to keep track of, how expensive my finance team's queries are versus my marketing team's queries. So things like that, right? This is like a conceptual idea, more about like authentication and access than anything else, right? This can be a single EC2 machine. It can be a cluster of EC2 machines. It's like, what is your compute resource? That's what you're logging into, that then accesses the storage layer. One other thing is like, Snowflake is a little fancy because it has this authentication layer. So really what happens is, before Snowflake performs the query, before it goes directly to the storage layer, the EC2 machine will go to the services layer, which is just like another EC2 machine. But this answers some questions for it. Like, okay, you want to access the users table. Are you authorized to access the users table? You want to, query this. Cool. I'm going to ask the query manager, and you want to query like recent users. I'm going to ask the query manager, first of all, it optimizes your query for you. So if there are any like performance optimizations, it will try to, optimize it before it executes it. It will also, look at where does this data live? Like, where do those partitions live? That's all here. And then, did you have the right username, password, that simple stuff. Other things it will do is, there is like some degree of like caching that goes on. So you can see you have memory, you have disk. So if you've recently, if you've asked for like the last 50 users, and you get it from the storage layer, comes back, and then you ask for the last 50 users again, it won't go all the way down here into S3. It will have cached like I forget how many recent queries, but per data warehouse, it caches like your 10 most recent queries. And so, meaning it will either live in memory or live directly on disk and on that EC2. All right, so it just makes it faster. So this services layer is basically, before it accesses S3, it tries to like perform some sort of optimizations for you, and it makes sure that you are authorized to perform the query. Okay, there is not necessarily any partitioning sharding requires, just dedicated. Okay, in Snowflake, we'll get to this, but Snowflake performs the partitioning for you automatically. You don't specify anything. It is automatically going to partition. You also do not need to worry about data skew with Snowflake, because it will repartition when it sees that. Really, I'm not sure. I'm not sure how it's working under the hood. I was going to say that I think it like basically is, a conceptual block anyway of like what that partition is. So if it sees like, okay, we have a bunch in this partition and not a lot in the other one, we will kind of like draw the line separately so that they're more even. That's what I'm guessing is happening, but I'm not positive. But you do not specify the partition in Snowflake. It does that for you. It's like even fancier than your normal partition, which we can talk about. Okay, so then we talked about this, the fact that it's just cloud based. So that's all I'm saying here is like the storage layer. What is it really behind the curtain? It's just S3. So when you see this, just think S3. The compute layer is just an EC2 machine. All right. And like I'm saying here, it can be a cluster of EC2 machines, can be one compute. You can also this is called scaling horizontally, right? When you have more, just add multiple machines. You can also scale vertically, which means on a single machine, add more computing power, add more hard drive, add more memory, etc. Right? And once you navigate, so it's really simple. It just has like data warehouse extra small or data warehouse medium, and then it tells you what is the compute, what is the memory associated with it. And then I say again, Snowflake can also do parallel processing. So if you have a cluster of computers, right, it is smart enough to basically access that admin, what do I call it, the services layer, and then decide, okay, in my cluster in this data warehouse, this node should be performing these queries, this node should be performing these queries, and then combine back the result. All right, so it's a fancy machine, Snowflake. I talk about let me see this question. Can we implement it in the way that Snowflake? Okay. That Snowflake has it set up for a specific database table, the policy mentioning only. I don't get. Can you reword that, Conwell?
Yeah, I was saying, as we saw, if you go back to the diagram again, the architecture diagram.
Maybe this one.
Yeah, this one works as well. So this data warehouse one, as you said, it's essentially an EC2 instance. So I'm pretty sure Snowflake has a lot more to offer, but at least from this looks of this diagram, can't we implement something similar like we have different tables in Postgres instance or something? And then for each table, we specify a policy
Well,
which
yeah.
essentially says only this specific EC2 can access it,
Well, you would say
which
only,
will,
yeah, only this user. Yeah, you'd say only this user can access it. Yeah.
yeah.
So it's not like it's. I don't mean that all your data is. You can think when you interact with Snowflake. Maybe I should kind of. I don't have a. I don't want to be able to log into it, but I can show you kind of some pictures, and you guys can sign up for a free account if you want to just interact with it. Um, but do I have it here? Hold on, data and post work 2024. You'll see, yeah, it just looks like you still do the same thing. Like you still create tables, you still load your data in, you specify the columns. So it's just like any other kind of. So here, this is probably a good one. Databases, schemas, and tables. So you can kind of see, this is what Snowflake looks like, right? So you can kind of see it. So here I'm logged in as the admin. This is I gave my warehouse a name, right? Remember what this warehouse is. It is an EC2 machine, right? That is in charge of kind of computing. Then you can see here I have these different. You can create multiple like databases the same way you have the concept of a database in Postgres, and then you can select all from here. I'm specifying the database name, the schema name, and then the table name, right? Limit to, and then here's the results. All right, and you can see it's storing some query details here. How long did the query take? Where was each component performed? Like, how did this take time? Part of it was accessing S3. Part of it was then going, probably like I don't know if it's then doing some other sort of computation and then giving you back the results, right? Maybe filtering or something and then giving you back the results. So yeah, I mean, and then you just type in your stuff and press play essentially. And then there's also like there's also like the same way we have Boto 3 for AWS. You can also just do interact with the Snowflake database from like a Python script that then you authenticate into Snowflake with. Like you don't have to do it from the interface. Um, anything else? That's the main stuff. Like you can see, we have these various tables underneath this schema, and then this is, I think actually this might be a database. I'm not sure. Um, and then here's the different columns. All right. So that part is the same, but under the hood, all this data is stored in S3. And then one other thing, I keep saying S3 and EC2, but when you sign up for Snowflake, it asks you, what do you want to be the cloud provider? So you can choose, Google Cloud, and it will use, like a Google Cloud instance and, like cloud storage, right? So you can choose which one you want when you sign up, and it's not like it's signing into your Amazon account. It's creating those services for you. So if you like then log into your AWS, you're not going to see the S3 service underneath. It's doing that for you. All right. The last thing, is then just about like Snowflake micro partitions. I put in like the actual reading. Uh, I did put in the reading there for you, but just like a couple points on it. Yeah, so like I kind of mentioned, normal partitions can have an issue with data skew, which results in disproportionately sized partitions. Snowflake will auto kind of like manage that. It will look for data skew and then repartition the data. And then remember we saw this with Redshift, the idea of like zone mapping, where it tells you for each partition what is the max value in there, what is the min value in there. Snowflake does the same thing. It will store that, and then in the services layer, it will query the services layer, see the zone map. Should I be looking at this partition or not? If I for this query. The other thing is, it's as I say, it's maintained automatically. You do not need to do anything. It does this for you out of the box, and it's partitioning both rows and columns. So rows meaning like data from 1990 will all be stored together probably, but then also if you're only querying the movie names, you're not loading up the entire row of data. So it's only going to be looking at like the movie names from 1990, and it calls these features. It gives its own. We don't want to charge you money and sound fancy. It calls this micro partitioning. Okay. And I put in their documentation about it. Yeah, here it is. Snowflake micro partitions. But you can kind of look through this. But that's what it does. You can see it doesn't do static partitioning. They're derived automatically. Do not need to explicitly define upfront. Right? They have micro partitions can overlap, which can help prevent data skew, I guess. Things like that. So yeah, these are kind of all the optimizations that Snowflakes give you. What are the main ones to remember? One, it's fully cloud-based, right? It hooks in directly to either AWS or Google Cloud. It's storing. Where is it storing the data? We have this isolated compute, so it's storing the data in S3. What's the benefit of that? It's cheap, right? What's the other benefit of that is basically we can scale our our data warehouses in our compute layer independent of the amount of data we have. Okay, we can boot these up, we can shut them down. We don't need them to maintain our storage. Okay, and then it has like this, icing on top services layer, which will, optimize for us. And then, right, this is how it knows where the data lives. So it queries this directly before doing the micro-partitioning. It has some nice things like it will cache results for you in your data warehouse. So that way it doesn't always have to access S3, things like that. All right. Cool. Yeah, so that's the main thing. I'd say, go through this. If you understand it, you can also move on, read through it, make sure you understand it. I would answer these. I put in some like questions. I'm trying to find them. Yeah, I'll find them. I put in some like questions about maybe. Oh, I think I'm looking at the wrong one. Yeah, I put in some questions about from last class. I would go through them just because it's good to like own this stuff. That way you feel comfortable talking about it in an interview and don't fumble too much of your words. And then I'll also do this, the CAP theorem. We kind of talked about it. The main thing about it is what I mentioned before. It's very hard to both be CAP theorems means like the idea is you're not able to both like partition and make your database both fully available and consistent. Okay, and the main issue is this: available and consistent. So we did kind of talk about that, right? The whole issue is, if you have, if it's partitioned, in this case it means like you're doing, it means across nodes, right? So it means, that you can think back to like our replica data. Okay, that's kind of, and the idea is if a node, if when it really what it means in the CAP theorem context of partitioning is if a node goes down, you're still good. How can you achieve that? Only if you replicate the data. Okay, so we're really talking about like replication with a CAP theorem because this partitioning part means if a node goes down, we are still kind of up and running, right? Now, that is kind of true, but if someone writes to this database, and before we copy over the data, this node goes down, we are kind of still available because we still have this node, good for us, but we are not consistent, right? So the CAP theorem really states you cannot have all three of these at the same time. And like I said, the real issue is both consistent and available, because in order to be consistent, one way that you kind of achieve this is you lock down availability, meaning as, say, the user updates their name or whatever, the date of birth or whatever they do, we lock that row across all databases until we kind of like have some degree of consistency, and then we remake that data. We say, okay, now you're able to read from it, right? So this takes a second, right, to make these these different nodes consistent, and that taking a second means that there is some time when they're not available. Okay, or you can choose that you don't need to be consistent, but you're just going to be highly available. What is some case you might be like, well, don't we always care about data? Well, we do, but let's say if you're like doing a chat application and say like there's an idea of like, well, the order, eventually this will be consistent, but maybe not right away. So maybe like, I'm kind of fumbling here, but it's like that the data is not super important if it's just like Facebook chat, and maybe eventually the chat kind of gets there or gets synced. Like that's the idea, I guess, is you can maybe imagine a scenario where we are like available, but we're not consistent right away, something like that. So based on the database, you kind of can prioritize different things, and it's not like you just like, I'll never be consistent. The idea is you're just not like ensuring that you absolutely all 100% of the time will be consistent. That's the idea. All right, so this is a CAP theorem. You probably won't be asked about it, I don't think, but if you hear it, just know like availability and consistency, those are the big issues, and then just draw two squares and just remember that like if I write to one, it takes a second for the data to get over to the other. And then you can do a deeper dive on it if you're so interested. But that's the idea. Really, the deeper dive is then different databases, like I kind of said, make different trade-offs about what they want to prioritize. If they want to prioritize consistency or if they want to prioritize availability and how they achieve that.